Okay, I'll say a few introductory remarks, and then we'll get underway. So thank you for coming and joining the first of, I think, 4 general hydrology sessions. So we have pretty good turnout for that. There's some other fairly hydrological or biogeochemical sessions throughout the week as well. So I encourage you to check those out and look at those talks. So my name is Pete Whittington, and I am the president of the hydrology section of the Canadian Geophysical Union. Barrett from Dalhousie is my vice president. He couldn't make this session. He's busy with convocation, maybe. I can't remember which, but I think he'll be chairing General Hydrology 3 later on this afternoon. So you'll see maybe both of us at some point today. And I'd also like to just acknowledge our First Nations. I won't get into the details there because we are coming from a very diverse group. Looking at the names on here, I think we are covering coast to coast at this point. So I'm sure you know your land acknowledgements for your universities as well as for your field research sites if you have field sites. So I'll get Brampton to share his screen and get that up and running. And so he'll be speaking to us about the drying of the Arctic and future changes, a case study from the Western Canadian Arctic. So our talks, we have 15-minute slots. So at about the 12 or 13-minute mark, if I don't think that you're close to finishing, I'll just unmute myself and say, okay, a couple minutes. And then at the time limit, I'll just cut you off so that people can be jumping around. It's important to stay on time. So go ahead, Brampton.
All right. Hello, everyone. So my name is Brampton Dakin, and I'm a second-year master's student at the University of Waterloo. The title of my presentation today is The Drying of the Arctic and Future Changes, a case study from the Western Canadian Arctic. So to begin, all of the work in this presentation is either based on field work done in Sigsig Creek or is a modeled interpretation of Sigsig Creek from the summer of 2021. So a little bit about Sigsig. It's a small subcatchment of TVC, and it can be found 50 kilometers northeast of Inuvik in the Northwest Territories. The size of the catchment is roughly 1 kilometer square, and as you can see from the figure, the catchment is dominated by alder and birch species, as well as peats, mosses, and lichens that have been lumped into the tundra classification. Mineral earth hummocks also litter the terrain and comprise as much as 50% of the catchment, despite being only half a meter to a meter in size. But first, and for context, the summer of 2021 was brutally warm and dry. So how do we know this, and just how anomalous was it? First, thanks to Brandon Walker and Jackson Cito for providing some of these figures, we have the end of winter snow water equivalent, or SWE, mappings for the catchment, as well as water balance. With the adjusted values, the water that was stored in the catchment throughout the winter was barely over half of the long-term average. This is important because the majority of water that is supplied to the catchment and which gets stored in the ground as it begins to thaw comes from the source. In fact, as high as 80 to 90% of stream flow for these catchments is directly linked to the source of water in spring melt runoff. A water balance for the summer also shows a large residual of 77 millimeters of water that left the basin. And part of this can be linked to the lack of precipitation, with the driest July recorded on record with only 4.5 millimeters for the month. According to Environment and Climate Change Canada, this was also the 7th warmest summer on record for Inuvik. So not only was the catchment set up for a dry summer from the get-go, but there was also no water coming into the basin from precipitation either. And what little water there was in the basin was leaving either as discharge or as evapotranspiration. So there are 3 overarching questions that I've sought answers to during my studies, but it's largely the second and third questions that I want to draw your attention to, as they're the focus of today's presentation. Specifically, how active layer development affects hill slope runoff and how microtopography influences this, i.e. hummocks and interhummocks. And secondly, can the physics-based model geotop capture this? For reference, the active layer represents the volume of ground on top of the permafrost that thaws seasonally during the summer and does not remain frozen year-round. There were a variety of sampling techniques used in the field to capture and observe changes both in water table and active layer depths, as well as soil sampling throughout the summer of 2021. Soil pits and coring were a large part of the peat thickness and mineral earth hummock studies, seen in figures 1, 2, and 4, and the frost probe was used to measure active layer depths along 18 transects that were measured on a weekly basis, seen in figures 3 and 5. The pop-up image here on the left is an example of a mineral earth hummock and its accompanying interhummock zone. So for context, and as it's being used in this study, acrothelm refers to the living portion of peat, and cadothelm refers to the dead and more dense portion of peat that underlies the acrothelm. The mineral earth hummocks are comprised of mostly high clay mineral soil, and the interhummock zones with a thicker amount of highly porous peat. You can clearly see how peat thickness is thin atop the hummock and becomes quite thick in the interhummock zone. There's also a noticeable difference in active layer depths between the two as well. On the right is a field of hummocks so that you can understand just how prevalent these landforms really are. This slide shows some of the results from my time in the field, specifically as it applies to peat thickness, hummocks, and their interhummock zone, as well as how this all relates to active layer development throughout the summer. The third image is an interpolation of a soil pit. This builds upon my earlier image and description of a mineral earth hummock, and is representative of almost all of the soil pits that were dug across hummock and interhummock zones. Within figures 1 and 2, there are 3 points that I want to briefly talk about. First, across both acrothelm and cadothelm, mosses had thicker peat components than lichens did. Secondly, there did not seem to be much of a difference across the high, mid, or low locations in the basin. There is a bit of a leeway to this though, as the thickness of the peat varies widely in the interhummock zone. Hummocks cannot always be seen from above ground, and as you can see in the third figure, the peat gets thicker the further from the hummock you get. So sampling peat thicknesses with this in mind is not necessarily consistent based on where and in relation to these hummocks you measure. However, there is a trend where mosses can generally be associated with interhummock zones and lichens with hummocks, as these features lie underneath them and was seen in almost every soil pit. This trend was further supported with the active layer depths collected throughout the summer. Third, even without accounting for the hummocks, there is a noticeable difference at the end of the summer for active layer depths measured directly under moss and lichen patches, a trend that is also true for hummocks and interhummocks. While not all of the hummocks can be associated with lichens over top, and vice versa with mosses over top of the interhummock parts, the inverse relationship between peat thicknesses and thaw depths still holds true and has been noted in other studies. Figure 4 is the culmination of all of this and represents the distinct separation between interhummock and hummock zones and active layer depths at the end of the summer. When you account for the identified hummocks and interpolating where these were based on lichens and mosses, there's this distinct separation between the two. Seeing these trends, it hints at the importance of beginning to map accurately mosses and lichens in these areas, especially when it comes to trying to understand the hydrogeological parameters of the basin. When you consider that the interhummock zones, which are comprised of the highly porous peat, compared to the mineral earth hummocks that are largely clay dominated, there are direct implications on how water and heat is flowing in the system. Thaw in the basin is uneven, and hummocks are at the heart of this. If you could correlate mosses and lichens as a proxy for hummock and interhummock zones, this could possibly be built into a numerical model to depict the tortuous movement of water in the soil and how it flows from the hills to the creek. So as what might have been hinted, the second half of this presentation revolves around the use of the numerical model geotop. It's a physically based hydrological model that is capable of solving for mass and energy balances and has the potential to model microtopography. The model domain is defined by input maps that cover everything from DEM, aspect, slope, soil and landscape types, to sky factor, as well as discretizing soil properties at its simplest. For the sake of the study and how geotop was used, there were two separate simulations that were run, a single soil domain and a double soil domain. The single soil domain acted as a validation data set against previous studies done with geotop in the catchment, where those studies averaged soil depths to represent the difference between hummock and interhummock zones, as well as decreasing the overall conductivity of the soils to further represent this, i.e. a single soil domain. The double soil domain is a more accurate representation of the soils in the basin, with mosses and lichens and the soils underneath defined and essentially acting as a proxy for the hummock and interhummock zones. These simulations were both run from the start of the summer to around when the ground began to start freezing again. So ignoring a bit of the random straight line in the middle of the maps, the single soil domain does show what was expected given the results from the previous studies with geotop, i.e. that the channel had the deepest thaw within the catchment and where the tundra portions were relatively consistent. Further, that the model does recognize ponding water in the creek, and typically active layer depths are deeper in these areas than elsewhere. Lastly, that the water table depths never went deeper than the peat layer specified in the catchment. The double soil domain looks rather more chaotic in comparison, but suddenly the open tundra areas that we know from field work that aren't evenly thawed start to reflect this. You can see the lighter colors dotting the map representing the hummocks and their deeper thaw depths, surrounded by the darker, less thawed interhummock zones. Outside of this, all of the trends that we would expect to see are still apparent, but now there's more distinction between hummock and interhummock zones. So which is more accurate? On the left, there's a 1 meter resolution classification of the basin that separates it into the green shrubby materials, red mossy materials, and white lichen materials. This map is the basin for all the land classifications that were used as input maps for geotop, and you can see a slight resemblance in the double soil domain figure, even though its resolution has been reduced to 10 meters. Lastly, I'd like you to recall the weekly thaw depths figure seen earlier in the presentation, and which you can see here. So on the left, we can see that the model in both the single and double soil domains is able to identify the difference in thaw depths in the basin with a distinct separation, although it's likely that for the single soil domain, most of this is the river channel. However, the double soil domain includes much more than just the river channel and its depths, and is reasonably more representative of what was observed in the field. Further, the ranges in depth are relatively accurate, especially so for the hummock depths. This is a good sign going forward, knowing that the model is able to identify and process microtopography. So to conclude, the summer of 2021, and warm summer, with conditions throughout the summer, as well as beforehand, setting the field to be an anomalous year, which could have drastic changes to hill slope runoff, as well as active layer development. Secondly, lichens and mosses have different thicknesses of peat under them, and this serves to influence both drainage as well as active layer depths. However, these features could serve as proxies for mapping hummock and interhummock zones, and the physically based model geotop seems to have the potential to accurately represent these microtopographies in its output maps. So first of all, I'd like to thank my supervisors, David Rudolph and Philip Marsh, for the opportunity to travel to the Arctic and to conduct the study. A huge shout out goes out to Brandon and Evan for their technical help, and to Robin, Tim, and Rosie for their expertise. And lastly, to Jackson Cito for somehow surviving 3 months in camp with me and for helping me collect all of this data. Thank you.
Okay, great. Thanks very much. Do we have any questions for the speaker? Any questions for Brampton? So I just had maybe a quick comment. When you separated acrotalm and catatalm, it might just be important to note that all peat is dead. So the acrotalm is not, or most of the acrotalm is not living. The only living layer is the moss right on the surface. Everything else is technically dead. So it's more that it's either poorly decomposed or not very decomposed or composed.
Yeah, that's a pretty important distinction. And a lot of the mosses in the catchment were like these really ropey mosses, so they were rather thicker than you might expect from just looking down on the surface.
Yeah, but if it's, I mean, if it's sphagnum, then it's really just the capitula at the top that's alive, right? So,
yep.
But, yeah, no, that was cool. So just remind me, how did you measure the frost depths? Just with a probe, or?
Yeah, it was a metal rod that was about 1 meter and 30 centimeters long. It never really was an issue because the thaw depths typically didn't get that deep. Although at the end of the summer, a few of them did start to get, very close to the end of what that probe could measure. which was a little disconcerting at times.
Yeah, but you can definitely tell when you hit the ice down there. I've done lots of frost probing as well, and you try to explain it to people, and you're like, you just know when you hit it, right? So
You really do. Yeah.
it's hard to write that into your methods, as you'll discover.
Yep.
A reviewer might ask, like, well, how do you know? Well, you just know.
Yep.
So.
Yep.
Okay. Do you want to stop sharing your screen and we'll get Daniel up and running? Okay, so we still have maybe 30 seconds, but I'll do the introduction now. So our next speaker is Daniel Peters, talking about why are perched basins in the Peace Athabasca Delta in northwestern Canada drying, revisiting the water balance. So we'll wait for the clock to tick over fully in case people are jumping sessions, and then we'll let you get going there. Coming to us from, is it sunny in Victoria right now, or is it raining?
It's still early in the morning, so the sun is trying to poke through, but mostly overcast.
Okay. All right, I think you're good to go, Daniel.
Thank you very much, Pete. As mentioned, Daniel Peters, a research scientist in Environment and Climate Change Canada as part of the Watershed Hydrology and Ecology Research Division. I wish to acknowledge my co-authors, Donald Baird, Spiros Belteos, will be giving a talk immediately after that's highly related to this presentation. Barry Bonzo, Jonas de Bieke, which I saw his name, he's in watching, Wendy Monk and Rajesh Shrestha. Why perch basins in the Peace Athabasca Delta drying? It's something we're revisiting as part of a new project. I did my PhD work way back in the mid-90s in the Peace Athabasca Delta, so it's a great opportunity to sort of revisit this entire question. Concerning geography and scale, the Peace Athabasca Delta is located at the confluence of the Peace River and the Athabasca River at the west end of Lake Athabasca in northwestern Alberta. If we zoom into the delta itself, it's a 6,000 square kilometer lake wetland deltaic complex. And in order to gain an understanding of the controls on the water balance of individual inland basins, or what we refer to as perch basins, we need to consider various scales. So when the basin is not connected to the main waterway, it's isolated and can be perched above, higher up on the landscape. When it does connect, then we have to look at the deltaic scale, connectivity, and what drives that connectivity. Then we have to go up to the continuing basin scale. And if we think of precipitation, then we go to synoptic scale to understand the annual snowpacks and rainfall, etc. So keep these geographic considerations as we go through the presentation. What's driven the revisiting? Well, in 2014, Indigenous people petitioned UNESCO World Heritage Center requesting that the Wood Buffalo National Park, which is presently listed on the World Heritage site since the early 1980s, as a protected area due to additional hydroelectric dams on the Peace River, oil sands development upstream on the Athabasca, and the general threat from climate change. There was a petition to change the designation from protected to in danger. And that was led by Mikisew Cree First Nation, supported by the Athabasca Chipewyan First Nation and the Fort Chipewyan Métis Association. In response to that, Parks Canada developed an action plan, which has a series of recommendations, and two key components relevant to this presentation is addressing environmental flows. In other words, flows that are necessary to maintain the ecological health of the deltaic ecosystem, and a monitoring and science. And so the two are conduct environmental flow assessments to sustain the PAD ecosystem. And equally important, in order to do the assessments, is an understanding of adequate baselines that need to be enhanced as part of the monitoring and assessment. A key component of developing an environmental flows is gaining an understanding of the hydrology, or what we're referring to as a hydrologic foundation. And today's talk will be on the bottom end of that scale, so the individual perch basins that are located within the floodplains. Depending on the connectivity, we now have a good understanding of the hydro period, which change in wetland water level over the year. Some basins are connected year round. So the one on the right here, what we refer to as open drainage. And so the water level will change in response to the adjacent waterway. Some are located just off a levee, what we call restricted, and some are located much farther inland, which are isolated and more often not perched at a much higher elevation. And depending on the distance from a waterway or the elevation, the connectivity can be either through ice jam events or open water flooding. And that little diagram shows you that in order to reach the much higher elevations, the combination of flows impeded by ice jamming is the most efficient mechanism for getting water into the highly perched basins. Hydroclimatic controls on the persistence of water in perched basins. We have a good understanding from previous work. Here's the basic water balance equation, floodwater inputs plus precipitation during open water season, snowmelt, PS, open water evaporation. And more often than not, groundwater is not a factor due to the very fine silts and clays and change in storage over time. And based on, and to give you a visual of the rapid changes, an example of one of the sites where it was bone dry, water table a meter below the surface in June 1996, and then the bottom image you'll see it was connected and flooded. So this could be a rapid change from terrestrial to aquatic, and then a much slower change back towards a terrestrial environment. And this example is 0.8 meters depth. Our simulations using various hydroclimatic scenarios was 4 to 9 years duration of water, of ponded water. We put together a little simulation here. Whoops. How come it's not starting? Just very quickly. I guess we have a technical difficulty here. It's not wanting to start the share. Okay. Fortunately, there's Landsat imagery that's available. We've obtained the global surface water extent that's available online. It's a product at 30-meter horizontal resolution. And what was supposed to happen is showing a change in sequence of annual images to show you the sort of the growing extent of surface water, which happens via connection, and the shrinking of surface water extent via losses of water. And unfortunately, that's not playing. Now, hypotheses to address the water balance and components. It could be increasing air temperature. As we all know, air temperature has a major influence on the form of precipitation. Rain versus snow, extent of ice season or the open water season for evapotranspiration, etc. Could be as a result of increasing evapotranspiration. Could be a result of decreasing precipitation. And the fourth one is decreasing flood frequency. So today, what I'm going to touch upon is the very simple. Our initial work is revisiting. We're at the start of this project. So I'm going to look at the precipitation minus evaporation of the P minus C index and to gain a better understanding of historical variability and trends in water loss. So the first result diagram I'm going to show you is the mean annual air temperature. Fortunately for Fort Chipewyan, there is data that goes back to late 1890s. So I present here 1900 to 2020. That'll be consistent for all the graphs. And so you can see that there's quite an annual variability in mean annual temperature around a mean of -2. Over the long term, there is according to the Mann-Kendall, there is a significant increasing trend. Especially you can more easily see it after the 1960s, but overall is about 1.5 degree per century. And again, that's an important controls on snow and ice, open water, and loss of water via evaporation. Seasonal potential evapotranspiration. In previous studies, we validated the Hammond equation, which is day length and air temperature based, which we validated over the season to be within about 5%. So it's a good potential evapotranspiration estimate algorithm. And here again, you can see there's quite some variability around the mean of about 459 millimeters of water loss per year. And there's no long-term, well, sorry, there is a long-term trend here because it's driven by air temperature. And again, there's quite a clear increase here in the graph that you can see after the year 2000. Whereas annual total precipitation, which is about 347, the long-term mean, there's no long-term trend. But if we look at the 11-year running means equation, you can see that in more recent times, since the 1990s, there is a noticeable decline in lower state of precipitation, and that combined with the increase in potential evapotranspiration certainly plays a key role in increased water losses back to the atmosphere. And the final results diagram I'm going to show you is the index of P minus E, precipitation minus evaporation. For that time period, there are no long-term trends that were found with the Hammond, but as you can clearly see in the diagram, there is definite wet and dry periods. So the early part of the century, fairly dry, minus 150 millimeters of net water loss vertically. The 1940s, 50s into the 60s is a wetter period. And then following 1990, quite a rapid decline in net water availability. In this case, we did a 21-year running mean to try and further smooth it out. And you can see again, since the 1960s, a general decline. So overall, there is an average over the 100-odd years is a net vertical loss of minus 112 millimeters or 11 centimeters. And we have measured that in the field. So these are realistic values. So in other words, a meter of water on average lasts about 9 years, if not replenished by floodwaters. And in the pictures I'm showing you here on the right, 1998, 2001, within 3 years, you can see a rapid loss of about 30 centimeters of water at one of our sites. Last slide here. So takeaway messages and next step. The P minus E is a good index for examining trends, change points, and cycles in water availability for perch basins. A combination of high temperature, in other words, potential evaporation, combined with less precipitation, can lead to rapid water level drawdown. There's been general decline since the highs in 1960s, unless reset by flooding. Revisit the perch basin water balance is our next step, is to simulate various hydroclimatic scenarios with more modern data, and revisit water surface extent. Whoops, sorry about that. Via remote sensing. The goal is to combine both a vertical examination of water level change and water level loss combined with surface area to give us 2 dimensions. and in order to get a better understanding of the spatial temporal changes and the perch basin hydrology that are influencing the aquatic habitat. And thank you very much.
Excellent. Thank you, Daniel. We've got about a minute for a quick question. If no one has a question, I have a quick question. So see if anybody pipes up. Oh yeah, here we go. Jason Lee. Oh, Andrew and Jason. Okay, so what do you know about the interactions between the lake and groundwater? Could this be a significant flux in whichever direction?
In the 1990s, we installed a number of piezometer nests and water level monitoring wells, and there likely are younger sites in the Athabasca Delta where there's coarser sediments that likely would enable subsurface water movement. But at the same time is that with every flood, an ice jam flood or a summer flood, it brings in sediments, and the water and the flood water recede, leaving stagnant water, so which enables the deposition of the fine grain clays and silts, which line these basins. So for the basins we've looked at up to date, the groundwater was a small component of the water balance. Having said that, there might be others that have greater importance.
Great, thank you, Daniel. There is another question from Jason, but I'll just comment that you can answer in the chat, perhaps, Daniel, so that we can keep on time. So Spiros, if you want to start sharing your screen. So our next speaker is Spiros Beltos, and talking about the effect of regulation on peak open water flows, the lower Peace River, Canada.
Hello, everyone, and thank you, Peter, for the introduction. This, you already stated the, let's say, the title of the talk, so I won't repeat it. But I'd like to acknowledge, first of all, my colleague and co-author, Daniel Peters, who presented the previous talk. By way of introduction, we know that in cold regions, generation of hydropower in rivers causes an increase in winter flow and a reduction in the late spring and summer flow. And a good example is a major Canadian river, the Peace, which has been regulated since 1968, following the completion of the well-known WAC Bennett Dam. This has had some implications to flooding and sustenance of lakes, ponds, and wetlands, which we generically call basins, as Daniel already discussed. The basins of the Peace Athabasca Delta, we sometimes quickly refer to it as PAD, and this is a very valuable ecosystem of national and international importance. In the past 50 years or so, there has been a relative scarcity of floods, raising concern and motivating many studies on the flooding mechanisms, including aspects of regulation and climatic impacts. We know now that spring ice jams are very effective in reducing extensive overland flooding and recharge of the various basins, but we only had 5 such events since 1968. At the same time, the recharge of basins under open water flow conditions has received less attention, and it forms the focus of the present study. And here we have a simplified map of the Peace Athabasca Delta, acknowledging the publication, where it came from on the side. And essentially here we see the Peace River flowing on the north side of the delta and emptying into the Slave River. And one important feature that informs this whole presentation is these connecting channels between major lakes of the PAD and Peace River. Now, ordinarily, this channel is flowing in the northward direction for being tributaries. However, when the Peace River is at high stage, but not necessarily at flood stage or over bank flow. They can reverse, and by so doing, they convey Peace River water, sediment, and nutrients back towards the delta and into the main lakes, but also into a myriad of small basins that are connected to these channels through sub-connecting channels. One more point I'd like you to note here is this location, Peace Point. Here we have a water survey of Canada Gates. It's a key hydrometric station that captures almost all of the flow that eventually comes down and enters the delta reach of Peace River, which begins at around this location. So how do we get summer recharge? And immediately I will say that I use the word summer here for convenience and acknowledge taking some license with respect to the calendar, because we get large open water flows in late spring as well as in the summer. So one obvious and effective mechanism to recharge the basins is overland flooding. It leads to extensive recharge within the Peace sector of the pipe. Another mechanism, which is produced by non-extreme but still sizable flows, can provide recharge to some of the basins via the reverse tributaries, as I mentioned in the previous slide. This is not as extensive, but such events are a lot more frequent than overland flooding. As Daniel also touched on, contributions to the basins by local precipitation, snowmelt, and groundwater are small and cannot keep up with evaporative losses. Therefore, without periodic river water inflows, many basins can dry up. So here I'll concentrate on the first phase of our study, which is overland flooding. So can we quantify the effect of regulation on the summer flow hydrographs? Yes, this can be done via the process of naturalization, which means trying to determine flows that would have occurred if the river had not been regulated. For this, we applied the lagged flow method, LFM. This method is based on hydrodynamic principles for river flow. It uses industry-supplied inflows to the reservoir of the Bennett Dam. And it's computationally very simple. The results compare very well with numerically model flows up to 1996, which were reported by those authors back in 2001. And here now we're getting into some results. In this graph, we are showing naturalized and regulated peaks for each year of the examined record, side by side. And you see that the black ones, that is the naturalized peaks, always exceed the regulated ones, which are the red. And we have calculated that on the average, the difference between the two is approximately 4,100 cubic meters per second, which represents 41% of the average natural peak. Another interesting feature here, and relates directly to the overland flooding, is that there are 3 natural events exceeding this blue line, which is an estimated threshold for overland flooding. So if we had natural condition, then we would have had 3 likely overland floods in the series. And of course, the red ones do not exceed that, and that agrees with experience because we haven't had any of those in the regulation period. If we want to look at trends of this time series, I have plotted here a couple of regression lines, which are simple linear trends, and they are mainly used for visual perception of the trend. And immediately we can tell that the black series or naturalized have hardly any trend, and there is a slight trend for the regulated series, which, however, for testing was found to be non-significant. And one more slide here is showing a hydrograph from the 1990 event, which is actually the highest on record. And immediately we see that the regulated hydrograph has two large peaks, both exceeding the flood threshold and lasting, the exceedance lasting for about 9 days. And this number can be compared to the extreme ice jam flood of 1974, which had overland flooding of about 2 weeks. So this is less than, let's say, this is more than 9 days, but the 9 days is a comparable number to the 2 weeks. And this is about all of the overland flooding, but we need to also examine recharge at lower flows, which do not go over the banks, but can produce reverse flow and recharge the basins in this way. And they are more frequent, so this needs to be examined. And to summarize, regulation has reduced natural peak summer flows by about 41% on the average. Natural summer peaks exhibit no temporal trend, and there is a slight increase, but not statistically significant in the regulated peaks. Overland summer flooding, which is unknown in the regulated period, could have occurred naturally 3 times. The flooding duration is comparable to that of ice jam floods. And for the future, we look towards examining additional hydrologic indicators relative to non-overland recharge of the various basins. I would like to acknowledge, or we both authors would like to acknowledge the support of our employer, ECCC, and also to express thanks to BC Hydro for providing the inflow data set and related background information. Here, if you wish, you can check those references. And this completes the presentation. Thank you, and I'm here for questions.
Excellent, thanks, Spiros. We have about 4 minutes for questions. So if there's anything, I don't see anything in the chat right now. Does anybody have any questions? None right now? Okay. So I think our next speaker is one of the poster presentations. Yeah, so we'll start that in a few more minutes. So. So Tariq, you're also a poster presentation, I believe, and then Ben, you're a regular presentation, and Dan Klong is another regular presentation, correct?
Yes.
Perfect. Okay. Yeah, so if anybody wants to run to the bathroom quick, then we got about 3 minutes, unless a question. Oh, we had one in the chat. Can Daniel play the animation? I don't know, Daniel, if you're still around, if we can, if you could get it to work. And if it's only a minute or 2, you could probably share your screen again.
Yeah, let me try. It's about 30 seconds.
Sure. Thanks, Martin, for that suggestion.
Can you see my screen?
Yep, and it is playing. Although I think you're playing it in reverse, maybe.
Yeah, I'm just trying to, I got it started before I
Yeah,
share
yeah.
the screen, just to make sure that, just hold on a sec.
Yeah, there we go.
Okay, here we go. It's only 30 seconds. You can certainly see the bigger water bodies shrinking and expanding.
And so this is
smaller-
August every year, or one point in
Yes.
time during August?
Yeah, it's preferably near August every year, the Landsat imagery, derived surface water extent.
How variable are the dates? Plus or minus a week, or plus or minus a couple of weeks?
It's within the month. It's not.
Oh,
the
there's
exact-
just one snapshot for the month.
Yeah. Yeah, and then the last image here is looking at the percentage of time that water current. So the blue is 100% and going to the red where it's a few percent. So there you can more easily see the shrinking and the expansion. And if we were able to zoom in to the inland areas where there's thousands of small wetlands with various connectivity, we'd be able to see various other colors. But,
So the one site, the picture that you showed, you know, July and then August, were you just not anticipating that site flooding, which is why the weather station was so close to being flooded, or?
That is correct. That's
Okay.
summer 1996. That's when BC Hydro found a sinkhole in the earth dam, and they were ordered to release 3 meters times 1,700 square kilometers of water over a 6-week period, and they recreated natural flow conditions where water reversed into the delta and it filled the large lakes, and the lake expanded into that research site. And Parks Canada called and said your site is flooded. And oddly enough, the physics plays in your favor. The battery was in a battery box on the ground, and it flooded so quickly that an air gap stayed on the terminals of the battery, and so the weather station logged everything during the event and after the event.
Cool. All right. So to keep us on time, our next speaker is Morgan, discussing estimating soil moisture storage using a geological weighing lysimeter. So these are going to be short, more lightning type talks for posters. So hopefully Morgan is still there. Yep, there she is. And then if you can, I guess you maybe have a short presentation or just a PDF of your poster or whatever it's going to be.
Yeah, I'm just going to share my poster here.
Great. Thank you.
Okay. Hi, everyone. My name is Morgan Broughton, and I am a second-year master's student at the University of Saskatchewan. And I'm going to be presenting on my poster, so estimating soil moisture with a geological weighing lysimeter. So soil moisture or water stored in the unsaturated zone is an important store on the landscape. It plays a key role in the exchange and partitioning of water and energy fluxes at the land surface. Representative measurements of soil moisture at field scale are needed to characterize hydrological processes and to calibrate and constrain weather and climate predictions. Agricultural practices also rely heavily on accurate measurement of soil moisture storage for crop health and vegetation productivity. But physically measuring soil moisture is notoriously difficult. It varies spatially as a function of the land surface and temporally as a function of dynamic drivers like precipitation, evapotranspiration, and melt events. And most conventional measurement techniques are constrained to certain scales. Traditionally, soil moisture is measured with point scale measurements, which provides high resolution information, but larger scale observation networks are needed to represent field scale measurements. Alternatively, larger scale continental measurements can provide coarse spatial averages, but it's often difficult to extract smaller scale soil moisture. The geological Wayne lysimeter provides an opportunity to measure soil moisture at field scale. These instruments use a saturated formations pore pressure response to mechanical loading from accumulation and depletion of water, which can be recorded in an observation well. The water accumulates on the surface and that creates a load, and this load induces stress. And that stress moves instantaneously with depth to the formation. Because the formation is much more compressible than the water in the formation bears the entire load, and there's an increase in pore pressure. This is indicated as an increase in water level in the observation well. As a result, observation wells completed in saturated formations can serve as giant Wayne lysimeters, recording total water storage as indicated by fluctuating water levels. So the objective of my research is to partition out soil moisture from the total water storage signal obtained from a geological Wayne lysimeter. I used a pore pressure record from a piezometer completed in a deep sand aquifer confined by 2 low permeability till aquitards at a research site in Duck Lake, Saskatchewan, in northern Saskatchewan. I then partitioned geological Wayne lysimeter derived soil moisture by subtracting local observations of snow storage and shallow groundwater storage. Next, I compared the geolysimeter derived soil moisture to point scale soil moisture to critically assess the performance of the geological Wayne lysimeter. So both the geological Wayne lysimeter soil moisture and point scale soil moisture captured seasonal patterns well, which you can see in figure 3, showcasing an influx of storage during melt and displaying precipitation and evaporation events throughout the summer months. However, there are differences in storage in the winter, and that's due to ice content, which was captured by the geological Wayne lysimeter derived soil moisture measurements, but not from the dielectric point scale measurements. The geological Wayne lysimeter derived soil moisture also detects more storage loss in the summer from evaporation, which may be a limitation with the point scale measurements that fail to capture the spatial heterogeneity of the landscape. The geological Wayne lysimeter derived soil moisture calculation also did not account for ponded water on the surface, so this could have led to an overestimation of soil moisture. These results show the potential use of using a geological Wayne lysimeter and local observations to capture seasonal soil moisture storage dynamics in locations where instrumentation is missing or sparse, and at a scale large enough to represent both spatial and temporal soil moisture dynamics. If you would like to ask more questions or you're interested in discussing my research further, please come to my poster discussion tomorrow at 11:45 Central Standard Time. Thanks.
Excellent, thanks, Morgan. And we'll get Tariq to show his short little lightning talk.
Great, okay. Okay, thank you. So my name is Tariq Dean. I'm a PhD student at McMaster University. There we go. So my research is part of a larger project here at Mac, looking at water security related issues at 2 different Indigenous communities. The one that I focus on is 6 Nations of the Grand River Reserve here in southwestern Ontario. And my role within the project is to look specifically at the impact of climate change on the community. So the results that we're presenting here are results that we have from modeling the Mackenzie Creek under different climate warming scenarios. So I'm just going to zoom in. So the Mackenzie Creek is a intermediate sized tributary of the southern portion of the Grand River. So the Grand River watershed is here in shaded pink, and then the Mackenzie Creek subwatershed is here in shaded black. And then the larger image here is a zoomed in image of the subwatershed. So again, the shaded black is the Mackenzie Creek, and the blue, the shaded black is the Mackenzie Creek subwatershed, and then the blue is Mackenzie Creek. And then the red outline here is Six Nations itself. So you can see that a large portion of the Mackenzie Creek flows through Six Nations. So it's important for the community to understand how climate change is going to be affecting the creek. And to do that, we are using the coupled groundwater and surface water flow model known as GS flow. And we're running simulations from 1951 to 2099 under two different climate change scenarios, representative concentration pathway 4.5, which is a intermediate level warming scenario, and then RCP 8.5, which is a higher level warming scenario. Zooming out. So looking at the model simulation, so here we have three different images. Panel A is monthly average of daily stream flow from 1951 to 2005. And then the important panels are B and C. Those are the future simulations at 30-year time intervals. So the time intervals are listed here. And what we see is that winter stream flow is projected to increase, but peak March stream flow and early spring stream flow is projected to decrease. In addition to late spring stream flow and summer stream flow experiencing little to no change in the future. And these trends are observed both for RCP 4.5 and 8.5. So in addition to this, we also looked at water availability measured by precipitation minus evapotranspiration. And that's illustrated here in this figure. So this is a monthly average of daily water availability. And what we see is that, again, this is at 30-year time intervals. So 2020s, which is 2005 to 2039, 2050s, which is 2040 to 2069, and then 2090s, which is 2070 to 2099. And what we see is that there's a increase in winter available, there's an increase in winter available water, and a small to no change in spring and summer available water. The change mostly occur in terms of spring and summer. The change is mostly under RCP 8.5. So what do these changes mean for the Six Nation communities? Well, if we look back at the map of the Mackenzie Creek, we see that as it enters into the Six Nations area, it has a much more meandering nature. So increases in winter stream flow as well as winter water availability might lead to not necessarily more intense flooding, but more frequent and earlier flooding within the winter season. On the flip side, because there is less water availability and lower changes in summer stream flow, there might be more water stress and more drought-like conditions within the subwatershed. Am I running out of time?
Yep, we're done.
Okay.
Okay.
Yeah, thank you.
Thanks very much, Tariq. Apologies, I didn't read your title out at the start.
That's okay.
Ben Pelto is our next speaker, talking about the historic and future post-retreat land cover evolution at Bridge Glacier, Canada.
All right, thank you. So yeah, my study area, I'm at the University of British Columbia, a postdoc there with Dan Moore, and I'm studying the Bridge Glacier. And as you can see here, the Bridge Glacier is a lake terminating glacier in the South Coast Mountains of British Columbia. If we flip to the next slide, you can see that the Bridge Glacier is located 2 hours north of Vancouver in the South Coast Mountains in BC. And the satellite image of the catchment, as I'm studying it here for the upper bridge, you can see with my mouse here, there's a water survey gauge on a stream just downstream of the lake that the Bridge Glacier terminates in. So this is a highly glaciarized headwater catchment. And this is part of the Bridge Seton hydropower complex that produces approximately 6% of the electricity for British Columbia on a given year. For this study, we're interested in land cover change and climate change in combination. Typically, most hydrologic modeling studies replace glacier cover with glacier retreat with either open or alpine land cover. And we want to understand how important it is to account for vegetation or soil development on these deglaciated areas. As you can see in this photo I took last summer at the field site, this red arrow, this red line that came in on the left of the lake here, that's where the glacier was from roughly 1960 to 1990 before it really started retreating across the lake. So a very dramatic amount of retreat has taken place. And this yellow line that came in here, that shows you the Little Ice Age trim line. So within the last 100 years, essentially, the glacier has went from occupying this whole part of the basin to pulling back to where you can see it here. So a really dramatic change. And if you look in the forefield at the bottom of the picture down here, you can see that the basin is revegetating. So we want to understand the hydrologic implications of this. Our primary motivations for what I'm presenting here are to map this land cover change to understand the historic land cover change and glacier change. And we also want to model the vegetation expansion below the Little Ice Age moraine into the future, like you can see occurring on the bottom of the slide here with these alder patches moving down slope. So as a starting point, we need to know where the glacier was in the past. So I started by taking some lichenometry dates combined with high resolution LiDAR hillshades to figure out where the glacier was around 1950 and the Little Ice Age maximum, which here I've roughly assigned a date of 1850. After taking those dates, I used some air photos from 1947 and 1964. Like shown here, we can see that this is the Bridge Glacier in 1964. The pink outline here, the mapped outline of the glacier at that point. Move forward, I used the Landsat archive after that in Google Earth Engine, at first manually for the 70s and early 80s. And then once we had shortwave radiation from the Landsat sensors, we could do it automatically following the method of Bevington and Menounos for every year from 1984 to present day. And so I'm going to run through this animation here a couple times. This is a Landsat animation of the Bridge Glacier draped over a DEM, and you can watch the retreat of the lake terminus here. Particularly if we watch this through a couple of times, you'll notice around 2005, the glacier really starts calving rapidly and breaking up and retreating at a very, very accelerated rate. And that's one aspect of the story. The other aspect, if we focus in on this black polygon that I drew in here that just came in, you can notice the vegetation development happening below the Little Ice Age moraine, which would be the right-hand or upper slope bounds of this polygon. And particularly around 2000, in the mid-2000s, you notice that area really starts to vegetate rapidly. And by the end of this, you can see there's quite a bit of green in that polygon. So a lot of vegetation development. So taking all these different data sources, we're able to produce extents like shown here from the 1850 or so up into the present day. And so we're able to assign dates. If we want to know what's the exposure age of a given pixel on the land surface, we can do that. If we look at the area change of the Bridge Glacier from 1915 to the present day, we can see that the glacier has shrunk from over 100 square kilometers down to below 75 square kilometers today. If we look at the lake, there was almost no lake in 1915, whereas the lake has grown quite large today. And as I mentioned before, and as we saw in that animation, around 2005, when the glacier calving really took off here, we can see that the glacier lake almost doubled in size from less than 4 square kilometers to nearly 8 square kilometers today. That's the glacier and the lake, but we also are looking at the vegetation. And to do that, we looked at NDVI. And so this animation here, again, this is that same slope I highlighted in the last animation. So at the bottom of this animation would be the lake. The brown line that just came in here is the Little Ice Age moraine, and you can really see the vegetation. Again, this green here is NDVI. You can really see the vegetation taking hold and developing rapidly over the last 40 years. So if we look at that, if we put it all together in one plot, we've got the glacier at the top, declining glacier area, increasing lake area at the bottom. And interestingly, vegetation and what we've classified as vegetated terrain versus bare terrain are almost identical through the record, particularly now, each occupying about 21% of the basin. So over this last 40-year period that I'm showing here on this plot, this basin has come to about a 50-50 split of glacier versus other land cover types. So still heavily glaciated, rapidly changing. If we look at developing a vegetation model, one thing we noticed in the field and in developing the model was that terrain was a large control on vegetation. So this is a map of topographic wetness index, which is essentially a function of slope and drainage area. So how much surface water would you theoretically be routing through a given location on the Earth's surface? And this is from that same slope I've been highlighting, that slope above the lake, below the Little Ice Age moraine. And you can see the horizontal lines on this plot here. Those are moraines. And here's an example of one of those in the field. Here's one of those moraines. You can imagine water coming down the slope, meeting one of these moraines, and then flowing around the moraine until a break point in the moraine. So stream channels do the same thing, even more dramatically. But basically what we were seeing in the field and what we've seen with this remote sensing data is that the vegetation establishes along places where water can, where there's water availability and where soil develops and then spreads from those locations like you saw in the animation. So for the vegetation model, we used an ordinal logistic regression model with exposure age from those glacier extent dates, topographic wetness index and slope from LiDAR digital elevation models, and NDVI. In this case, we used first neighbors. So if you're interested in, say, this red pixel is your pixel of interest, first neighbors would be these 4 black pixels around it. And we do that with a 1-year lag, so from the previous year. And that would be the predictor in the model, the NDVI from your given pixel's neighbors. And then we predict 3 different NDVI classes, essentially bare terrain, low or moderate NDVI, so shrubs or such, and then greater than 0.6 NDVI we call high vegetation. And our field surveys show that these areas were typically shrub jungles, basically willow, alder, and in many cases evergreen trees or other tree species. For us validating the model, we trained the model from 1984 to 2014, and then tested the model from 2015 to 2021 and found a misclassification rate of around 12%. So overall works pretty good. If we watch the model here, again, at the center here, we've got the glacier lake, and above and below the slopes below the Little Ice Age moraine. The green here is that high vegetation class, so basically a shrub jungle, we'll call it. And then the yellow is a lower vegetation, and then the gray, and very little is left at the end, is the bare terrain. Now, that's what we've been working on to date. Moving forward, we want to inform we want to build a hydrologic model. And to do that, we need to understand the volume loss from the glacier. So we'll train the model with recent glacier volume loss, like taken from the study by Romain Hugonet et al. This is aster imagery, just showing you the annual rate of height change over the Bridge Glacier here for recent years. We can also look at calving flux data that has been estimated in the past for this glacier. Shown here, the gray bars are the estimated calving loss, And don't need to worry about the absolute magnitude here, but these blue bars are the total volume loss of the glacier each year. And one interesting thing you notice is that there was a really rapid calving that occurred in the mid-2000s. Yet, irrespective of that, the total volume loss of the glacier has continued to increase into the future, which is quite interesting. And in fact, you can see the lake here. This is a photo from 2014. The lake used to be full of icebergs. Well, once the glacier, then icebergs. And around 2014, it peaked. And then now the lake is essentially barren of icebergs. We also need to project the glacier forward. If we're going to be projecting future, using future climate projections and our model of future vegetation, we also need to know what's the future glacier area. To do that, I'm using the Open Global Glacier model to model the bridge glacier as shown here. It's a simple flow line model. You can model the ice thickness of the glacier and then feed that with climate data to grow, or in this case, shrink the glacier. I haven't done it yet, but I did run a simple 100-year commitment run. So basically using today's climate, what happens to the bridge glacier with no climate warming? And you can see the glacier would have been at the right-hand side of the page. And now the glacier occupies this area between the bed and the glacier surface. So a retreat of far more than half of the glacier length and far more than half of the glacier volume by the end of the century, even without climate change. But we'll be doing that in a more robust fashion soon. In conclusion, vegetation development, as you can see here on the slope with alder and evergreen growing in and moving down the slope from above the Little Ice Age moraine where there's intact forest, that's controlled by topography, exposure year, and proximity to established vegetation. And our vegetation model predicts the future vegetation expansion with a misclassification rate of around 12%. And one thing that I haven't mentioned is that the glacier is likely close to leaving the lake. You can see where my mouse is here, that there's a sharp kick up in the slope of the glacier. And so we expect that that will be the end of the glacier lake and the end of the glacier as a calving glacier. Thank you.
Excellent. Thanks very much, Ben. That's startling. Some of the retreat there. If you have any questions for Ben, I suggest you put them in the chat so we can basically get right back on time. Ben, I'm not sure if you're available to stick around and check out the chat, but really interesting and some great animations there. Our next speaker is Dan Quang Dai, talking about using automatic optimization methods to calibrate irrigation parameters in NOAA MP model in North China Plain with census irrigation amount. Can you stop sharing your screen? I think I can actually do that. Yeah, there we go. Thanks, Ben.
Okay, let me share my screen. Just wait a second. Just wait a second. Sorry. What a minute. Okay, find the system.
Are you able to share your screen?
Yeah. Let me find this. Okay. Can you see my screen?
Yep.
Okay. It's okay, good morning, everyone. Thanks for your attending my presentation. I'm a PhD student from Institute of Atmospheric Physics, Chinese Academy of Science. And my research title is Impacts of Anthropogenic Activities on Terrestrial Water Cycle, Part 1, Census Data-Based estimation of irrigation or Martin-Enos channel plain. Firstly, I want to thank for my colleagues from National Center of Atmospheric Research and the University of Saskatchewan. GRIS data is used for detect terrestrial water storage change, and this map shows shifts in total freshwater between 2002 and 2016, as measured by NASA's Gravity Recovery and Climate Experiment satellites. It shows how water storage is changing and what the various causes are. In more than 40% of the cut part, the water shifts partially or largely with anthropogenic activities. That included the North China Plain, where irrigation have relied heavily on groundwater pumping. However, what the pumping groundwater used for in North China Plain? The North China Plain is a major food producing region in China. Since 1970s, irrigated agriculture in China has developed rapidly. Agriculture plays the largest part in water usage sector, and groundwater is a primary source in fresh water supply. Groundwater is the world's largest freshwater resources and is critically important for irrigation and hence for global food security. Unsustainable groundwater pumping exceeds recharge from precipitation and rivers lead to water table depth drops, and especially in intensively irrigated areas. Groundwater pumping will have devastating effects on ecosystem and lead atmospheric interaction. So when the groundwater depth is shallow, groundwater acts as a buffer that directly modulated soil moisture and surface water through a relatively slow two-way water exchange. When groundwater depth is deep, groundwater pumping brings groundwater into surface and further generated redistribution of terrestrial water resources. Previous irrigation research mainly focused on the North China Plain, North India, California, and American Southwest. Many researchers have investigated irrigation depends on evaporation, soil moisture, runoff, temperature, groundwater, and precipitation. However, there is some shortcomings in irrigation research in China. First one, not many observations, and irrigation. Second, irrigation is highly variable in space and time, and previous irrigation study focused on sensitivity test, not real situation in China. And first, irrigation modeling seldom consider groundwater resources. So my question is that this study, we want to improve modeling irrigation amount by using parameter calibration and quantify irrigation amount as the graded scale, and evaluated irrigation depends on basis of real situation. In this study, the research domain is North China Plain. So this figure is spatial distribution of area equipped for irrigation for 2000 in mainland China. The data is from historical irrigation data. The box in this plot indicates the modeling domain, and the red line indicated the North China Plain used for regional analysis in this study. The North China Plain is the heartland of China, consisting of the provinces of Beijing, Tianjin, Hebei, Henan, and Shandong. The rich soils in this region, in this area, were formed by sedimentary deposits from the Yellow, Huai, and Hai River, providing excellent conditions for agriculture. As a new effort of the NORP model, dynamic irrigation scheme has been incorporated into the high resolution client data assimilation system. This irrigation scheme includes 3 irrigation methods: flooding irrigation, sprinkler irrigation, and macro irrigation. In China, agricultural irrigation is mainly based on flooding irrigation. Parameter optimization problems are faced with serious computational efficiency problems. Parameter optimization is very expensive in terms of computational resources, and its cost is usually closer to increase of parameter numbers. Regarding our research target, we choose 3 sensitive irrigation parameters in irrigation modeling. For example, IRR, MAD, FI loss, and FIRT, FAC. And the parameter calibration and the data assimilation are used for tours to minimize the model error. In this study, we apply a general calibration method in NORP model to improve modeling irrigation amount. This global optimization method, known as SCUA, has shown promise as an effective and efficient optimization method for calibrated parameters. After building a platform of automatic calibration parameter in NORP model, we carry out irrigation parameter calibration work in 48 prefectures in this study. The difference in spatial resolution of the model grid and census data. So we need to do some spatial downscaling of irrigation water amount. In the process of downscaling water use intensity, uncertainties of different irrigation map source are significant. So we need evaluated 3 commonly used irrigation map by CMOS irrigation area, irrigated area data in next step. We choose 3 common used map. The first one is GMIA, and the second one is MER 2018, and the third one is GRIPC. The default irrigation map applied in NORP model is GMIA irrigation map in China. Regarding to total irrigated area, GMIA dataset, GRIPC dataset, and MER dataset over estimated total irrigated area compared to CMOS total irrigated area. So the next step, we make comparison of irrigated area at province level and prefecture level between different maps and CMOS data. The estimated and the reported irrigated area for 5 provinces are also given. And GRIPC dataset and the MER dataset suffered from significant disagreement with the CMOS data. GMIA dataset and the CMOS data at the province level agrees reasonably well. So we focused on them. We focused on the irrigated area. Then we focused on the irrigated area of 5 provinces: Beijing, Hebei, Henan, Shandong, Tianjin, located in North China Plain. Note that there is a significant agreement at prefectures level between GMIA and the CMOS irrigated area, compared with GRIPC and the MER dataset. So all in all, we in the end, we apply GMIA irrigation map to irrigation modeling in the next step.
We have about a minute left, maybe a bit less.
Okay. The parameter calibration, and this is calibrated result about 3 irrigation parameters. And the range of the IRR-MAT parameter inputs to the parameter automatic optimization is 0.2 to 0.8. The final optimization result shows that IRR-MAT parameter in most areas is between 0.6 and 0.7. And the FI loss parameter is different in spatial distribution and is generally high. And the FIRT, FAC parameter calibration results are between 4 and 7. This figure shows the simulated spatial distribution of irrigation amount without parameter calibration. The magnitude of irrigation amount is around 100 millimeter, and which is generally lower than the CMOS data. In some places with irrigation activities, the simulated irrigation amount is rarely or even 0. And the spatial and the scatter plot of the simulated irrigation amount and the CMOS data, the fitting degree of the model output after calibration and the CMOS data is 0.7, which is much higher than the default one.
Okay,
So,
I think we're going to, that was sort of a full 15 minutes. So we're now running a few minutes
okay.
over. So thank you very much. If you have
Thank
any questions, please put them in the chat, and we will introduce our final speaker of this session of General Hydrology 1 is Mohammed, talking about challenges in hydrologic land surface modeling of permafrost dynamics, impacts of parameterization on model fidelity. So if you can stop, there you go. And then Mohammed, if you're there, yep.
Yeah, I'm there. Can you hear me?
Yep.
So I'll start sharing my screen. So can you see my shared screen?
Yep, we're good to go.
Yep, thank you very much. Good morning or good afternoon, everyone. This is Mohammed Abdulhamid, a PhD candidate at the University of Saskatchewan. And let's start my talk on challenges in hydrological surface modeling of permafrost dynamics by some quick definitions. What's permafrost? It can be defined as any ground material that stays at or below 0 Celsius for at least 2 consecutive years. The active layer is a layer of soil on the top of permafrost, as shown on this graph to the right, that doesn't stay frozen all the year and subjected to a seasonal thawing freezing cycle. Second point is that why permafrost status is important for us. Why should we monitor it? So as the earth forms, permafrost thaws, and this thawing of permafrost releases carbon to the atmosphere in different form of carbons, carbon dioxide and methane. The amount of carbon that currently stored in permafrost is almost twice as the amount of carbon currently stored in the whole atmospheric system. So we could say that permafrost thaw will dramatically alter Arctic and subarctic landscape, impacting human infrastructures, plant and animal communities. But hydrologically speaking, water fluxes, storage, flow buses, stream flow, seasonality, stream flow or runoff generation mechanism, all these hydrologic aspects are sensitive to the state and the dynamics of permafrost. So modeling wise, modeling permafrost, or the land surface components of the Earth system model can be considered as a valuable tool to investigate the potential impact of climate change on both the hydrology and climatology, as or due to the fact that they simulate the coupled evolution of heat and water across the soil vegetation atmosphere interface. But still, building a model with high fidelity and accuracy to represent permafrost is a challenging task by 3 challenges. First one, as normal or as common in hydrology, the data unavailability, especially over large domains to describe the spatial heterogeneity. The second challenge is to initialize the model state variables of this model that has a large thermal and hydraulic memories. And lastly, the structural inadequacy and complexity, represented by different process interactions, huge number of meteorological variables needed to force the model, and the number of free parameters. This point will be the main theme of this talk, with 3 specific research objectives. The first one is to understand the combined impacts of climate forcing and parameter uncertainties on representing different important signatures of permafrost, and then to assess the sensitivity of these signatures to the perturbation of land surface model parameters, and lastly, to investigate parameter identifiability. So this flowchart summarizes our methods or our framework by which we will tackle this problem. We start by defining our model, which was mesh model that embed the Canadian land surface scheme, or class in short. In this flowchart, there are 3 inputs. Let's start by defining the study area. We had 3 experimental sites within the Mackenzie River Basin, characterized by different permafrost characters and climatic conditions as well, which were Havoc Back Creek, underlain by continuous permafrost, both Worst Creek, underlain by discontinuous permafrost, and lastly, January Creek, underlain by sporadic permafrost. The thermal profile data were obtained from different reports from Geological Survey of Canada and shown here. The second input for us was the forcing data set. We're talking about uncertainty in forcing data set. So we had to use 3 forcing data sets that were watch forcing data era interim, watch forcing data era 5, and watch forcing data bias corrected by GEMCABA. These three products has a varying spatial resolution, temporal resolution, and coverage. And lastly, the parameter values or the parameter sampling. Each model or each configuration has 29 parameters. So we sampled this parameter using a star technique, ending up with around 26,200 model evaluation for each case. So the next step would be to evaluate the ability of each forcing product to replicate the observed permafrost. And that was done by the uncertainty analysis. This schematic shows the different output that can be extracted from a single simulation. We will focus on 3 of them. The active layer thickness that I defined at the beginning of the talk, T minimum and T maximum. This is the minimum annual temperature envelope and maximum annual temperature envelope. And we will assess the quality of replicating these 3 variables using the mean absolute error and the bias. This figure shows the PDF and CDF for the bias of T minimum, the bias in replicating this T minimum across different the 3 sites and the 3 forcing data sets. So we are in our view the best performing data set should be the data set that yields a distribution with a mean around 0 and the minimal range of the PDF, which was satisfied by the last column of subplots, which for F W F D E I G C. And this table lists summarizes different PDF and CDF for all our experiments. Each cell start by a number this is the mean of distribution, and then between brackets the minimum and maximum of the distribution. Entities in red, this is the best performing experiment, and as we can see here, most of the best performing experiment was forced by our last forcing data set, which forcing data era interim bias corrected by GEMCABA. So we decided to use it for the subsequent analysis. So the second step was to perform a global sensitivity analysis. We utilized the VARS, which was the variogram analysis of response surface. This figure summarizes or presents the ratio of sensitivity of the 29 model parameter for each experiment. And then these parameters are grouped into a family of parameters based on the function that they play in our model. So as we can see here, or we can notice that the snow cover parameter, or ZSNL, was almost sensitive among all the experiments. Each row of subplots, the first row of subplots shows the sensitivity analysis for T minimum. The second row shows it for the T maximum, and the last one for the active layer thickness. So we can notice that ZSNL or snow cover parameter was sensitive among all the experiments. The second observation that 2 drainage or runoff parameters, DD and X slope, this is the drainage density, and the tile slope, these 2 parameters played a moderate influence on the sensitivity. And lastly, for the active layer thickness, another 2 parameters or 3 parameters were sensitive in this case, which was the S depth or the depths to the bedrock, and to canopy parameters related to which were the leaf area index in winter and the roughness height. This table summarizes the sensitive parameter under each criterion, T minimum and maximum and ALT, and then the union of the three of them. Then the third part of the assessment was to perform parameter identifiability analysis. We performed the classical identifiability analysis. We start by defining the behavioral thresholds. But notice that since we have three criterion, we were looking for the thresholds or for the parameter set that can collectively fulfill this threshold at the same time. I mean, we're looking for parameter set that give good replication of T minimum and T maximum and ALT at the same time. So we ended up with few parameter sets ranging between 7 to 89 out of 26,200 parameter set that we have initially. And this plot shows from this plot we can see the identifiability of parameter. I highlighted the sensitive parameter that have a sensitivity ratio of bigger than 10% red, and include that those has sensitivity less than 10%. And as we can notice that not all the sensitive parameter, for example, ZSNL, were clearly identifiable. Among all experiments, other parameters, slope could be identifiable, and so on. Not only that, we focused on one of the experiments, and that was the Jamari experiments for the mean absolute error, and we explored another permafrost variables. In the first 4 subplots, we we compared the envelope of this 13 parameter sets simulation to the observation for ALT, mean annual ground temperature, depth at the bottom of permafrost, and DZAA. We had a good replication, or our envelope encapsulated the observation in a good way, but this was not the case for mean annual ground temperature and PB, subplot B and C. And then for subplot E and F, this is the bias and the mean absolute errors for the 2 envelopes that we already talked about. And I'd like to focus on this subplot G, that represents the date of maximum thawing. That can be representative to the thawing freezing cycle. It's clear that we have a huge uncertainty bands of 150 days. And there are, this 13 parameter set were distributed into 2 clusters. Again, here at different timestamps, we evaluated our simulated envelope of temperature profiles to observation. We have a good agreement for T maximum, the maximum annual temperature envelope, but it was not the case for T minimum. Some years we have an overestimation or warmer T minimum. Some other year we had an underestimation, and some other year it was okay. So what's the take-home messages from this work? I'm presenting it in form of questions and answers. So the first question, which forcing dataset enabled the model to represent different signatures of permafrost? In our case, it was, sorry about that. It was which Gymkhana, which forcing data area entry bias corrected by Gymkhana. The second question, do different permafrost signatures impose trade-offs in the choice of forcing datasets? The answer is yes, as we saw that for this dataset, for watch forcing data Gymkhana, it enables representation of some aspect of permafrost dynamics while being inadequate for others. The third question or point, which model parameter are sensitive or primarily responsible for the uncertainty in prediction? We had 2 groups of parameters that describing heat insulation at the vegetation soil interface, and those that control the run of generation processes. Are these sensitive parameters identifiable? Unfortunately, it was not the case, as some of these sensitive parameters were not clearly identifiable. And lastly, to what extent will reducing the uncertainty in those parameters lead to a reduction of uncertainty in prediction? As we show in our last experiment that we have a good replication of ALT, T minimum and maximum, other descriptive factors of permafrost dynamics were not appropriately reproduced. For the acknowledgements, this research was financially supported by NSERC, IMBCC, and SERC. You can access the preprint of this work via scanning this QR code. It's currently under review in the Journal of Advances in Modeling Air Systems. This is a list of references mentioned in this presentation, and that's everything from my side. Thank you very much.
Excellent. Thanks, Mohammed. That was exactly 15 minutes. So if there's any questions, then I'll suggest people just hang on for a second to ask them, but we'll let people leave for a quick break or for their lunch. I noted in the chat that the Young Hydrologist workshop will be starting in about 7 minutes or so. So if you have any interest in that. General Hydrology 2 will start in about an hour and 15 minutes or so. And then we also have the CGU HS AGM on Friday evening. So there was an email went out to the membership late last week, I think, with the agenda and documents that you might need for that. So hopefully you'll be able to attend that. I'll stay on if there's any questions, but if not, have a good break and thanks for attending. I don't see anything in the chat right now and no one's unmuting themselves. So I think we're probably good, Mohammed. So have a good break, morning, afternoon, evening, wherever you are.
Thank you.
Bye-bye.
Bye.
Oh, and thank you, yeah, for helping with the hosting.
Thank you.